Hello everyone, thanks for your patience. We're a little bit late today, but thanks for hanging in there and thanks for joining us. We had quite a turnout today, so thank you so much for supporting us. So today what we're going to talk about is, steady shear viscosity versus extensional viscosity. So the most common, when people use viscosity in the general sense, it's always referring to steady shear. But there are other types that exist, specifically extensional. So we wanted to elaborate on that, and specifically in the context of our technology. So our technology is microfluidic technology. So we're going to talk about it in general and then also specific to how we can measure with the v-VROC technology, both steady shear and extensional. So let's get started. Okay. Okay, sorry for the pause there. I'm having a little technical trouble with the presentation today. So I think we're finally ready to get going. Okay, so when you think about viscosity, viscosity in general is going to characterize the resistance to flow. And the general definition of viscosity is that it's the ratio of a stress response to a particular type of deformation, a rate of deformation, because we're talking continuous deformation here. So that's the very general definition. Now you can vary the type of deformation that you apply. And this is where the different definitions of viscosity come into. So when you apply a steady shear flow, then this is where you measure a steady shear viscosity. And when you apply what is referred to as an extensional flow, and we're going to elaborate what that is shortly, then you're going to be measuring the extensional viscosity. And so it's the difference really is, it is very straightforward really, and it's just the type of deformation that you're applying. So for RheoSense, we work in microfluidics. And so our way of distinguishing these two types of flows is to modify the flow channel geometry. And for steady shear flows, what we have, and this is what we use for our m-VROC, we have a uniform flow channel. So the dimensions are uniform from the inlet to the outlet. So you just have, along the length of the channel, a steady shear flow. To introduce the extensional type of flow, what we introduce into the flow channel, into the microfluidic flow channel, is midway between the inlet and outlet, we have a hyperbolic contraction and expansion. So it's this hyperbolic contraction and expansion that is going to introduce the extension in the center of the flow channel. Okay, so let's start with, so we want to understand, specifically, what steady shear is versus the extensional. So let's talk in detail about what happens in the standard flow channel or the uniform flow channel, which gives us the steady shear. So in this instance, and the best way to visualize this is if you're looking at basically a fluid between two parallel plates, the base plate stationary, top plate being dragged along at some velocity. And so in this instance, the viscosity, is to say shear viscosity, is defined by the shear stress divided by the shear rate. So shear stress is just the force that's required to drag this plate divided by the area of fluid in contact with the plate, and divided by the shear rate. The shear rate is basically just, it's the velocity gradient across the channel. So in this case, it's quite simple to calculate. It's the velocity divided by the gap between the plates. So this just defines the viscosity. So the distinction with the steady shear is that because you have no slip boundary conditions at the walls, and by no slip boundary conditions, this means that the fluid adjacent to the wall is moving at the same velocity as the wall. So that means the base plate, which is stationary, the fluid immediately adjacent to that is not moving, whereas the plate above, which is being dragged along, the fluid immediately adjacent to that is moving at the same velocity as the plate. So this sets up a gradient in the velocity perpendicular to the flow. And so that is what introduces the shearing motion. So what happens now with this type of motion is that adjacent fluid elements are basically being forced to slide past each other. So this is why oftentimes shear viscosity is thought of as being indicative of as an internal or molecular friction, because you're basically forcing things to slide past each other. So you can imagine why this is why different materials have different viscosities. It's going to be a different experience for example, low molecular weight solvents to be slid, for the fluid elements to slide across each other, versus say a solution of macromolecules where you have very high molecular weight polymers or proteins. And also for systems like that, where they're large enough, if molecular weight gets large enough, you can even have a velocity gradient across the molecule. So then you can deform these molecules as well. So this is why the viscosity is so dependent on the sample that you're measuring, and it's very informative about the sample that you're looking at. But the general thing to take home here is that steady shear, because of this velocity gradient perpendicular to flow direction, introduces the shearing motion, and you're considering fluid elements being sliding across each other. So kind of like an internal friction. So our technology for measuring this, we use our standard flow channel, as I stated. It has the same dimensions across the length of the flow channel from entry to exit. And just to review for anyone who's not familiar with our technology, we refer to our technology as VROC technology, viscometer rheometer on a chip. And so what we're combining are microfluidics and MEMS, microelectromechanical systems. So what we have here is the case where we have the flow channel, and beneath the flow channel are 4 silicone pressure sensors. And we're controlling the volumetric flow rate through the channel, and we're measuring with these sensors the pressure drop across the channel. So because we're controlling volumetric flow rate, we use this along with the geometry, the basically parameters, dimensions of the flow channel, to calculate shear rate. And we use this pressure gradient that occurs across the flow channel to calculate stress. And then this defines the shear viscosity, dynamic shear viscosity. So stress divided by shear rate. And it's a uniform channel. And so you should make a note of what the pressure profile looks like for our steady shear measurements in our flow channel. It's going to be linear across the board, because this is going to be quite different than the pressure drop that you're going to see when we introduce the extensional flow channel. So the calculation for this is quite simple, and the pressure profile is going to be linear across the channel. So I also wanted to point out, since ultimately we're going to sort of compare this issue when it comes to the extensional flow channel, you always have to be concerned for rheological measurements, whether or not you're introducing turbulence or secondary flows. So the theory that you use for calculating the viscosity, and viscosity is always calculated, is assuming that you have laminar or unidirectional flow, meaning that the fluid is moving in all one direction. So you don't have any eddy currents or recirculating fluid in the system, because that will artificially increase the viscosity because it adds extra resistance. So what we need to consider is the Reynolds number under the flow conditions. So for the steady shear flow in this rectangular slit flow channel, if we have a Reynolds number less than or equal to about 2300, then we have this laminar flow, and we don't have to be worried about any artificial increases in viscosity due to the secondary flows. So this is just the expression for Reynolds number, which is really relating inertial to viscous forces. And when inertial forces get too high, then you start to see the onset of this turbulence. So this number really just depends on the properties of the fluid, density and viscosity, the velocity or flow rate at which the fluid is moving, and then some characteristic length scales of the flow channel. So you don't need to worry too much about the exact expression, just realize what it depends on. And so what I wanted to show for one of our flow channels where you can achieve one of the highest shear rates for our systems, what the Reynolds number would be for something very low viscosity at a very high rate in one of these systems. So this example here is just for water at 25 C, and we're using our chip that has a 20 micron channel depth and a width of 2000 microns. And the max flow rate that we can achieve with this chip for the water is about 18,000 microliters per minute, which corresponds to a shear rate of over 2 million. So what we see is for the Reynolds number for these measurement conditions is only on the order of about 300. So this is quite significantly lower than the onset of turbulence. So turbulence is generally highly unlikely for steady shear measurements in our flow channels. Now when we get to talking about the extensional channels, we'll see that this is quite different. Onset of turbulence is much more problematic for that system. Okay, so that's the general concept of the steady shear, and then what you need to be concerned about when you do the calculations, particularly in terms of the onset of secondary flows and how that can impact your measurement. So now when we consider the extensional flow channel, as I mentioned, the way we achieve this is to introduce a hyperbolic contraction and expansion midway in the flow channel. Now this contraction is going to, so we talked about in steady shear, what's important is that you have the velocity gradient that is perpendicular to the direction of flow. But now when we introduce this contraction expansion, because the volumetric flow rate is going to be constant, as you move into the smaller channel, into the contraction, linear velocity is going to increase. And so now we're introducing with this contraction a gradient in the velocity in the direction of flow. So this is going to be your extensional rate. And this is sort of an example on the left here. This is a microscope image blown up of the extensional flow channel. And then also the velocity of the fluid as it enters the flow channel. So you can see that as it enters the throat or the channel, you're getting an increase in the viscosity and you're getting a constant extensional rate. So now this gradient now in the direction of flow is going to act to stretch or elongate the fluid element. So this is the different type of deformation that you get by introducing the contraction. So that's the big distinction between the two types of viscosities, is the shearing motion versus the stretching or elongation of the fluid element. So I also want to point out that our system in reality is not a pure extension. And the reason this is the case is that you're still pumping the fluid through this flow channel that has no slip boundary conditions. So the no slip boundary conditions still apply. That means you're still going to have velocity gradients that are going to be perpendicular to the flow field, and you're still going to be generating some shearing. So there's still a shear contribution present. So it's really unavoidable unless you are able to set up a system where you have perfect slip at the interface, which is difficult to do and really not possible here. So you have to bear in mind that this measurement is going to have a shear contribution. However, I'll talk about a little bit later where you can subtract this off for certain types of fluids quite easily if it's important for you to remove that from the calculation. Okay, so a little more specifics now. So we had seen before for our steady shear flow channel, the simple linear pressure drop that occurs across the 4 pressure sensors that are positioned beneath. Now things are going to look a little more complicated, but we'll walk through it and I'll explain how you can handle it. So now this is just a schematic at the bottom here of the flow channel with the hyperbolic contraction in the center. So now we still have 4 pressure sensors spaced along the flow channel, but we have 2 pressure sensors prior to the contraction and 2 pressure sensors after the contraction. And so when we look at the pressure drop as a function of position, we see this larger drop that occurs as we move through the contraction. And this is the region that you're going to look at when you calculate the extensional viscosity. Because actually, you can calculate the shear viscosity just by looking at what happens between pressure sensors 1 and 2 and 3 and 4. But the extensional information is really coming from the drop between P2 and P3. However, you need to do a little manipulation of the data, because there are some limitations on the pressure sensors and where they can be placed. So the pressure sensors cannot be placed at the exact entry and exit of the contraction. So what we need to do is extrapolate to the entrance and to the exit. So extrapolate this curve for P1, P2, and the curve for P3, P4, so that we're looking only at the pressure drop that occurs across the contraction. And so this is the pressure drop that you're going to use to calculate the extensional viscosity. So I wanted to point out that unlike the standard flow channels, our standard flow channels, we have much more variety available there. So you can get flow channels that vary the height of the flow channel and also the range of the pressure sensors, or the max pressure. But the extensional flow channel, the dimensions are fixed. It's only the pressure that you can vary. So the dimensions for all of our extensional flow channels will be given here in this little table. Okay, so if you're interested in the exact way that this is calculated, what's going to be relevant, as I mentioned, so as your fluid element is going into the hyperbolic contraction, it's going to experience some rate of extension. And that is just going to be dependent on the volumetric flow rate and the dimensions of the flow channel, which are defined in this schematic here. So it's basically just the length of the contraction, the height of the flow channel, the width of the channel in the contraction relative to the width of the channel before and after. It will also be dependent on what we referred to as the Henke strain, which is just basically the strain that the fluid element feels as it's in the middle of the flow channel. So with these parameters and then the pressure drop across that hyperbolic contraction, this is how the apparent extensional viscosity is calculated. So the way it's written here is slightly different than what we saw on the previous slide, because now I'm including so delta PC, which is what we talked about on the previous slide, is the corrected pressure drop across the contraction. But now I'm saying that if you're able to, you can remove the viscous or steady shear contribution that occurs in the flow channel. However, the only way to do this is if you know the steady shear behavior if you are able to measure the steady shear behavior of your fluid. And there are analytical expressions for this for Newtonian and power law fluids. But beyond that, it becomes more complicated to try to correct for this steady shear contribution to the pressure drop in the contraction. Okay, so let's look at an example of some real data that we have, a real pressure profile that we measured in the extensional chip. So what you can see is we were able to extrapolate the pressure drop between pressure sensors 1 and 2 to the entry point of the flow channel, and then also extrapolate the pressure drop between 3 and 4 to the exit of the flow channel. And from this, we calculated this delta P sub C. And knowing the other parameters, basically the Henke strain is fixed by the geometry. It's fixed basically by the dimensions of this contraction. Knowing the flow rate that we applied, because we've controlled this by the syringe pump, we can then calculate the extensional rate and calculate then the extensional viscosity. So, and then I also wanted to point out that using the equations for the standard channel, you can calculate steady shear viscosity using the pressure drop between pressure sensors 1 and 2 and 3 and 4. And it's actually quite informative to look at this profile when you're collecting your data, because deviations in these two pressure drops prior to and after the contraction can be indicative of the secondary flows that we're going to talk about in a second. So this is quite useful to view all the information. Okay, so just like you can calculate a Reynolds number for the standard flow channel, you can calculate a Reynolds number for the extensional chip. And again, it's just going to be the same general parameters, but now the characteristic velocity and the hydraulic diameter are going to vary because now you have different channel dimensions. So the expression, though, can still be determined to be dependent on the fluid properties. This is a steady shear viscosity that's incorporated into this on the flow rate and then the dimensions of the flow channel. And what you can see here is that it's been shown experimentally that at a much lower Reynolds number, you will see a transition to turbulent behavior, or you'll have problems with secondary flows at a much lower Reynolds number. And so you're much more likely in this system to have, this what looks like extensional thickening artifact. So it's always very good when you're analyzing your data, and we'll see in a second some data where I think this might be happening. It's always good to look at it with a critical eye and try to understand what you're seeing. Okay, so here is, so we want to go into some sample data where we're looking at both, we've taken the same samples and we've measured extensional and shear viscosity. So the first example that we have here is xanthan gum solutions. And so xanthan gum is a high molecular weight. By high molecular weight, I mean in excess of about 1 million polysaccharide solution. And we have these in various concentrations. And because they're so high molecular weight, even at these very low weight percentages, we see significant rheological modification, which is why they're quite commonly used for that purpose. So the top plot here is the extensional viscosity in Pascal seconds as a function of the extension rate. And below, on the equivalent samples, is the steady shear viscosity as a function of shear rate. So now the first thing to notice is that the extensional viscosity is higher than shear viscosity, and this is generally true. The stress response to an extensional flow is higher than a shear flow in many systems, most systems. And you can see that for both cases, there is shear thinning initially under both steady shear and extension. We were able to go to much higher rates for the steady shear, so we were able to go in excess of 100,000 inverse seconds. And what we've seen is that there is no sign of any turbulence or secondary flows even above 100,000 inverse seconds for the steady shear measurement in the standard channel. And this is what we expected based on the Reynolds number calculation. However, when you look at the extensional viscosity and at much lower rates, so in the vicinity of 1,000 to 2,000, we start seeing this, what looks like thickening behavior. Now, we can't tell for certain, what exactly is happening in the system unless we have some sort of flow visualization. But if we go back to calculate the Reynolds number, for example, the green curve, the lowest concentration curve, as we just described with the equation on the previous page, we see that at this point here, where I'm indicating with the arrow, that the Reynolds number is about 10. So this is where we might expect to see the onset of turbulence for the sample. And so we can't rule out that this is a turbulent effect as opposed to a true extensional thickening. And you can see that this effect is most pronounced for the lowest viscosity or the lowest concentrated xanthan gum solution. Okay. So another example of comparing the extension versus shear viscosity. I prepared a poloxamer solution. So poloxamer is just a amphiphilic triblock copolymer. This has a polyethylene oxide, end blocks, and a mid block of polypropylene oxide, the mid block being more hydrophobic due to this extra methyl group. And we're using the specific poloxamer P407, which is just defined by its particular block length and overall molecular weight. And we were looking at this at 14% in PBS. The reason I chose this is because because poloxamer solutions will self-assemble in aqueous solutions, and their behavior will change as a function of temperature. I can change the viscosity and change the behavior from Newtonian to non-Newtonian just by changing the temperature. So I can get a variety of behavior with one solution just by changing temperature. So if you look at the shear viscosity as a function of temperature, you can see that this is temperature sweep from 20 up to 70 degrees C, and we can see that as we go from 20 to 30, we hit a maximum in the viscosity. And so I wanted to see, the shear versus extensional viscosity at 20 C and 30 C. So again, we have extensional viscosity on the top as a function of extensional rate, and shear viscosity as a function of shear rate on the bottom. And we have it for the two different temperatures, the 20 and 30 C. So what we can see is in this case, there's no indication in either type of experiment that we have an onset of turbulence. And the qualitative behavior is similar. So the 20 degrees C viscosity measurements tend to be independent of the rate for both types of deformation. And then, although we couldn't get to quite the same extensional rate as shear rate for the 30 degrees C experiment, it does seem to look as though thinning is starting to occur in both experiments. So in this case, the qualitative behavior was quite similar, and we didn't see any issues with secondary flows, onset of secondary flows. And again, the viscosity is higher in the extensional flow, which is what we generally tend to expect. Okay, so that's just some sample data just to show you that, how the data differs for the same samples in extension versus shear. So just to summarize, the viscosity is a defined property, and it's really defined just by the type of continuous deformation that you're applying, whether that's a steady shear deformation or an extensional deformation. And so, in our case, we achieve one versus the other by looking at either a uniform flow channel or a flow channel with the hyperbolic contraction expansion. Now, steady shear is really much, much more common and much more used in practical applications because it's much easier to achieve, and it's much easier to interpret. There's more theories available for its interpretation. Extensional viscosity is true that it's less commonly measured because it is more difficult to achieve and interpret. However, I wouldn't neglect it as an option, particularly since for our instrumentation, it's just a matter of changing out the flow channel within the existing instrument. And because it has a lot of use in a variety of practical applications. And although, as I mentioned, our testing with our extensional chip is not a pure extension, but rather a mixed flow, that's generally what you're going to see in practice too, is, you're generally not going to eliminate the no-slip boundary conditions. So you're always going to have, in many situations, this mixed extension and steady shear flow. So just some examples of where you might use this, the extensional viscosity in real life applications are, for example, flow through a nozzle, such as in inkjet printing, any sort of spray applications, which would be similar to the nozzle. There's been some discussion on whether or not when in the blinking cycle that there's, as the eyelids separate each other, that there's also some extension occurring. So in ophthalmic formulations, it might be interesting. And then also, many of our customers with the extensional chip work in the oil industry. So I will stop there and thank you for joining us and participating, and I'll check to see if there are any questions from the audience. And of course, if you don't have questions now, I know that you can certainly contact us later if you think about things. Okay, so there's just some questions about getting a recording of this and the slides. And so yes, everyone who signed up can get access to the recording so they can review it. And then also the slides can be made available to you. So we also have a question about, can we measure polymer melts? So that really depends on the exact system. So obviously certain polymers will flow at lower temperatures than others. So you would have to be able to load the, okay, so you're talking about a PET blend. So I don't know the exact transition temperatures for that, but what you would have to be able to load the sample into a syringe, which then would be pumped through the flow channel. So if you can load it at a temperature where this is possible, then yes, you could do melts. We do have temperature control on the instrumentation, and we do have a high temperature system that goes over 100 C. But we don't have the same capabilities. We can't, yeah, 280 C is a bit too high. So at the moment, 280 C would be too high for this type of testing. We can only go to maybe 110 C at this time. So your particular melt I don't think would work because we can't get to that temperature, but I think certain ones would if they have lower transition temperatures and you could actually load them. The diameter, so we have a question about some of the dimensions related to the diameter of the orifice with extensional flow. So I'm thinking you're asking me about, let me scroll back here. Let me know if this is right. So I scrolled back on the slide so that I have the list then of the dimensions of the channel. So this width here, W sub C, is 400 microns, and then the channel depth is 200 microns. So I'm not sure if that's what you mean by the orifice, or if you meant the inlet and outlet. Okay. So we have a question then that's asking about, so for Newtonian fluids, when you're dealing with a pure extension, the ratio of viscosity referred to as the Troughton ratio of extensional to steady shear viscosity, depending on the specifics of the extension, is going to be about 3 to 4. For this particular flow channel, these values, we don't get the values 3 to 4. We get values that are higher, something closer to, if you don't correct for the steady shear component, it's close to 80, and if you do, then it's down maybe 60 to 70. And there are various arguments as to why this is. So if you want to contact us, I'll make a note of your question, and I can send you some references where people have measured in the extensional flow channel. But it is very common that it is much higher than other types of measurements. And the speculation is, so I've sort of gone back to the image where we have the contraction, the microscopic image of the contraction, and then what the velocity profile theoretically would look as it enters the contraction. But in reality, if you look at some of these references, they've actually measured using velocimetry, the velocity as it enters and exits the flow channel. And what they've seen is that the extension starts much sooner than expected and goes higher than expected. So this then is potentially the cause for this higher Troughton ratio for the hyperbolic contractions. And so again, if you're interested, I can direct you to those references and some of those measurements and why they think that is the case. But our flow channel does not give that 3 to 4 ratio. It gives something higher, and that's actually commonly seen in the literature for hyperbolic contractions, flows and hyperbolic contractions. Okay, maximum. So we have a question about the maximum syringe volume for the e-VROC, and I believe it's 10 milliliters is the maximum volume that we have for that. Okay, yeah, so 10 milliliters. Okay. Well, okay, there's a follow-up question then that can you go as high as 25? So my colleague who's sitting next to me was telling me that we have customized in the past. So right now we don't. What you would need is, because we control temperature, and temperature is very important in viscosity measurements, you would need a syringe jacket to fit the 25 milliliter syringe. And we don't consistently make those, although this is a custom option if that's important. Okay. Okay, we have another question here. Let me just read quick and think. So we're getting a question about when you have a situation like a real life application, I'm assuming, where the fluid is experiencing both extensional and shear flows. The question is, what is the relevant parameter when you're trying to predict the performance? And ideally, what you would want to do is try to set up an environment that's going to mimic reality, right? And try to impose both shear and extensional. So in this case, our hyperbolic contraction in our flow channel is going to apply both of these. And so this, getting the uncorrected viscosity could be a useful parameter, because it is hard to separate them out and try to use only one versus the other. So I don't think that's a straightforward question to answer. I think ideally you'd want to try to look at the resistance to flow and something that might mimic reality that is really shearing and extending the fluid, which could be the hyperbolic contraction. That's possible. Let's see here. Okay, just reading some more questions. So there's a question. So I had mentioned when we were discussing the idea that our ratio of extensional to steady shear is much higher in the hyperbolic contraction than you would expect in a pure extension, because of the fact that this extensional strain would happen much earlier than we expect. And so someone's asking that what would that mean to, when you're looking at the pressure drop between P1 and P2, which are the pressure sensors prior to the contraction. So, looking at the data, and I can also send you, I'm not sure if you're the same person who also wanted the reference, but I can show you the data for where this starts and the way our pressure sensors are spaced. As I mentioned, there are some limitations on how they can be spaced, and so they're spaced a certain distance prior and after the channel. So I don't see that there's any disturbance between pressures 1 and 2 due to the hyperbolic contraction. It's very clear when we have secondary flows that there's a disturbance there, but I don't think a flow in the laminar state has any disturbance because of this early extension. Okay, so we have some questions then also about choosing the specific parameters that we chose. And I actually don't have a good answer at the moment, for the exact dimensions that were chosen. I think to some extent they were chosen because of the ability to place the sensors before and after the flow channel. But there's probably some details that I'm not aware of. So I can certainly look into that. I wasn't part of that design, so I don't have all the details, but I can certainly look into that and try to get back to you if you would like. And then we've also we've recently had more interest in extensional flow, and people have, we've talked about, there are real life situations where there is both extension and shear, and they have specific parameters that they'd like us to try to make. And so we have talked to people about, modifying the parameters to work. So that may be an option moving forward. Of course, there are still some limitations because of the placing of the silicone sensors beneath. Okay. Okay, I'm just reading some more questions here. Okay, so there's a question about studying colloidal systems near the glass transition. No, we have not. I haven't had any colloidal systems available, although I do think that would be an interesting case to look at. Okay, someone's asking about there's a question about which types of samples would show less shear interference in an extensional measurement. So I assume by shear interference, and you can correct me if I'm wrong, that you mean the shear contribution to the pressure drop in the hyperbolic contraction. So obviously when you have something that is going to exhibit a very high extensional viscosity versus something that's going to be very low in the shear case, then the difference would be very small. So it would be extreme cases where the Troughton ratio is, by the nature of the polymer system or whatever it is quite large. So someone's asking about measuring a polymer in aqueous dispersion. And they're concerned that it might be get stuck in the hyperbolic contraction. So we can provide you all the dimensions again, and then the general rule is that any dimension of particles or aggregates would need to be less than 10% of the smallest dimension. So there should be no problem with testing so long as that's the case. So someone's also asking about getting presentation slides sent to them directly, or do you have to download them from the website?
So you will get a direct email giving you access to the recording. Unfortunately, the recording is a large file, which is why we convert it into a YouTube link. So all of that will be emailed to you directly.
Okay. Let's see. So there's another question here about investigating low viscosity polymer solutions. And is this meaningful? So I would say that so long as you can operate, well, I mean, I guess maybe this. Let me step back. I think low viscosity polymer solutions can be meaningful. The example pressure profile that I gave you was actually for a low viscosity polymer solution. The polymer was very high molecular weight, though. It was, I think, around 7 million. So in that case, although the shear viscosity was low, the extensional viscosity was higher, and it seemed to resist the onset of turbulence. So I think you can, and even the onset of turbulence may not be a problem for you if for example, your application is under flow conditions where that may happen, and you may want to see, how that impacts the response of the fluid, and that may be relevant for your application, the onset of turbulence or not. So that's not necessarily a problem. So let's see. I think I missed one. Let me jump back here. Okay, so someone was asking, so the question was, when the polymer coalesces, is it very hydrophobic? So I'm not sure if you're referring to the poloxamer that we were talking about. So if so, I'll explain that, and if not, maybe you could clarify. So the poloxamer is basically a tri-block where the mid-block is more hydrophobic. So what it will do in solutions above a particular concentration, and also as you increase temperature, it will form spherical micelles. So that's the type of microstructure or self-assembly that it forms. So the mid-block, which is more hydrophobic, will associate with other mid-blocks forming these spherical micelles. So hopefully that answers your question. Okay. So I think I've gotten to everything. But again, I just want to let you know that if you have a question later, please contact us. We'd love to talk to you and work with you and help you to understand the measurements and how they could help. Okay, we'll wait a couple more seconds here. Okay, so I think that's, hopefully I got to everyone's question. If not, as I said, please contact us. We'd be happy to communicate and work with you. Thank you again for joining. We appreciate your support. And yeah, so I think we're going to end it here. Thanks again.